take an AP Chem, and that's a good thing. We do apply to Chem starting with the first lab, because osmosis and diffusion work based on chemicals. The ones we predominantly use in this class are covalent, ionic, those are basic simple bonds. We'll talk a little bit about nonpolar covalent because that's going to cause cells to react differently to solvents than polar covalent. About the only polar covalent molecule we'll talk about is water. We'll talk about it a lot. And if you need reminders on this or what kind of bonds these are, let me know. I'm not going to spend time in it. Brush up, get your Chem notes, take a look. They're pretty straightforward. And then, of course, hydrogen bonds are a big deal because those are going to be packed full of potential energy for us. If you remember from Chem, hydrogen is extremely reactive. So we're going to have to be careful with it. It's going to be based out all the time, but it does have a lot of potential power for us, so we'll be using hydrogen bonds all over the place for energy sources. Those are the big ones there. Okay, let's talk about water some more, and let's see how you'll do. I've got this little thing to see for those of you guys who've got the traits down. I'll go through again quickly. Okay, let's see how you would do with a tiny little fun quiz. So what do you think? Okay, true or false? Water contracts or gets smaller when it freezes.
False.
Okay. Do. Water has a high surface tension.
True.
True. Condensation is water coming out of the air.
True.
True. More things can be dissolved in sulfuric acid than water.
False.
False. Rainwater is the purest form of water.
False.
Yeah, I'm going with the majority. It takes more energy to heat water at room temperature to 212 than it does to change 212 water to steam.
False.
I like the confident one. False! If you evaporate an 8-inch glass of water from Great Salt Lake with a salinity of about 20% by weight, you'll end up with about 1 inch of salt.
True.
You know, those are one of those great questions. It's got to be true. There's too much stuff out there. Okay, seawater is slightly more basic than most natural fresh water.
True. True.
And raindrops are tear-shaped? What do you think? It doesn't matter. Just what do you think?
True.
Okay? And water boils at lower temperatures in Denver than it does at the beach. Okay, let's see what it is.
100%.
It's 50%. Okay. Oh, come on, Internet. Don't stop now. We'll never know. There it goes. Okay, so we were right first time, obviously. Yay, false. We know if it got smaller, what would happen to ice? It would sink. It expands, it gets larger when those molecules slow down. If it got tighter or tinier, it would be heavier and denser, it would sink. Really a problem for organisms that live in water that freezes in the winter. Get the bottom of the funnel and, oh no! Okay, got the next one right too. There is a high surface tension caused by pretty much the hydrogen-hydrogen bond reaction. That is certainly something important to organisms that take advantage of walking on the water like little water striders. Or the idea that it has higher surface tension, so it slows slightly the rate of evaporation, which is nice. Okay, the next thing you also got true, which we figured condensation is water coming out of the air, and you can see it when you reach the dew point. It's easy to reach the dew point when it's humid, so you'll see your glasses sweat if you have ice in the glass or a cold drink. You can see it form on the outside of the drink. Okay, so far so good. Rainwater is false because we know there's a lot of properties in the air that water picks up because of its dissociation properties, aka universal solvent, so it tends to not be the purest form. Got that one right? More energy. That's not true. Takes the same amount of energy, just a different phase. Got that one right too. Salt Lake. Yeah. Okay. Great. Never gonna ask you that. Slightly more. Yes, it is. Has to do with the salt. Uh-oh. Not teardrop.
I knew.
You probably thought it was, because if it's out of here, will it be teardrop? Yeah, because adhesion will have it stick to what? The faucet. So ever so slightly, if you could slow it down. These would be teardrops. Why will it not be teardrops in the sky? Yeah, this has where it sticks to. So it won't change its shape up there or in the atmosphere. But anything you pour from, its adhesion properties will cause it to take that little elongated teardrop shape. I'll look at you learn something. And you got that right at the end. Yes, it does take lower because of the pressure. Not too shabby. Good job. And again, I'm not going to ask you those. It was just more of a fun thing. So again, I kind of went through and I looked at the ones I'm going to And I decided to put that in surface tension, even though it's really a property of hydrogen bonds. But let's go through and make sure we're all on the same page, because you can find 8 traits if you look online, you can find 6 traits if you look online. I start with color because it really is the most important trait of water in terms of its molecular structure. You could certainly argue for a life point of view that it's abundant, that's necessary. So yeah, you can talk from a different perspective, but just in terms of molecular or chemical makeup, its polarity is awesome, because what that allows it to do then is have some of these other traits, because the oxygen in one molecule is attracted to the hydrogen in another, positive, negative charge. Which one's negative, by the way? Slightly negative?
Height.
Oxygen is slightly negative, and the hydrogen stays positive, so they attract each other. That gives us cohesion, which means water likes other water. Clearly, that's going to be important, because isn't that going to allow us to form puddles and pools and lakes, which is kind of critical for all the aquatic things that take care of that. If we didn't have cohesive properties and one water repelled other water, gosh, could you imagine? You'd never, the rain would hit the ground and just evaporate so much more quickly. It'd be more like alcohol. When you spill alcohol in lab table, how quickly it evaporates, because it would be repelling each other. It's stuck. Especially your fish. Adhesion, it also tends to like to grab hold of other substances. That, again, is because of polarity. Because if water is on a substance that is slightly negative itself, it will be attracted by the positive hydrogen. If it's on a substance that's slightly positive, it will be attracted by slightly negative oxygen. So that polarity allows it to stick to other things. Again, this property is great for organisms like plants. Think about plants that have to move water from where to where? Roots all the way to leaves. They don't have muscle tissues like we do to facilitate that, so they have to move it pretty much one cell at a time until they can do something to pressure. Wouldn't it be nice for a plant to be able to pull water up into the cell and then have that water stick to the inside of the cell? Because going against gravity? Yeah, it's a great property for plants to take advantage of. Surface tension. Keely gave us that, and I decided, yeah, it is this property of the hydrogen bond. So it's sort of stealth property, if you will, but it is going to be important in our planet, because this property, again, combined with the other ones, or because the other ones, help us to maintain large bodies of water, which of course regulate temperatures, provide habitat. You all know this exists if you ever done a belly flop? Oh, yeah. God, that hurts. Yeah, not good. And hopefully, again, most of you have seen this, because Amber Bio. Isotopic heat. Obviously, you can also talk about that as high latent heat. That is important because, again, if we didn't have that water, could you imagine what the temperatures of our planet would be? I mean, it's not surprising that places that are around coasts have much more sort of desirable and predictable weather within a more normal range. The farther away you get from that, even though it's still regulated by the amount of water on a global scale, it makes the planet livable. And part of it is because the solar heat coming in is being absorbed by water, and then of course water stays stable. So you imagine if it didn't, your pools would boil in the summer. So you can't go swimming today, water's boiling. Oceans boil. It is either a solvent, again, because of polarity, it's attracted to other solutes. And by the way, let's just review, a solution is something dissolved in water. Solutes are what are dissolved, and the solvent is what was doing the dissolving. For us, in almost all biological systems, what will our solvent always be? Water. If you're not in a biologically sort of contained arena, you could use all kinds of things for solvents. Acetone, gasoline, paint thinners. Obviously, they will kill cells. Can't use those. So, acids, etc. So we have to use water, which works well. Great, because of the property. And then there's the issue when that lattice structure, just meaning if you look at the molecules, they make sort of a nice little geometric pattern. The molecular structures of oxygen and hydrogen together. When they slow way down, they tend to sort of spread out. A lattice, if you picture something you can grow plants on, it's got this nice gappy or airy or spongy sort of feel to it. In other words, it's not solid or dense or compact, because because of that, ice does float, which is very important for lots of different things, including but not limiting to temperature regulation of our planet, habitat for those organisms that live in areas where it's crushed if you try to hibernate in the water, that's where they all go. Fish, turtles, amphibians, they're all in there. There's a lot of rate of flow a lot because of temperature, and they just wait till it's thaw. It's the converse is true, all those things can be crushed. And again, clearly you could expand upon this and put, high latency, talk about some other ones, but these are the big ones that will tie directly to biological clock. Good? Oh. Do we need to talk about osmosis and fusion? And in terms, just to make sure you understand, we deal with really three prefixes, hypo, hyper, and iso. And then we deal with really two suffixes in here to describe things. Tonic just means something is in the water. So if I put salt in the water, you don't use the word osmotic anymore, you use the word tonic. Because osmotic is clearly dealing with just pure water. So if I want to talk about the amount of just water in an area, and it is higher than something else, of course you have to have comparisons to use higher or lower than. So you could put any of those three prefixes in front of tonic if you're talking about a solution, or osmotic if you're talking about just the water. We'll talk more about water's potential as a free, pure substance next week. We'll do some investigations in the lab. Check on a little demo here in a minute. Diffusion, osmosis, passive, active. Right. Those do require energy. Cool.
Passive means just it doesn't require any energy to do, and active means that you have to use energy to do it.
Right. So if we were talking about, so usually osmosis is assumed to be passive because it's going in concentration gradients from high to low. If you wanted to talk about active movement of water, you have to use different terminology, like active osmosis, or it implies that diffusion and osmosis are both passive, meaning they happen because of concentration gradient, not energy on the system. So we can certainly talk about what your body doesn't want to happen or what does stop that. Okay, so let's talk about a couple examples here. So let's say that, and by the way, because more than or less than is in terms of two areas, in other words, I can't say to you, oh, this has more than, because what's your question? More than what? Not if I got a big bucket, it doesn't have more than anything. So, and what are we talking about? So we're always comparing. For our class, the two environments will always be inside the cell and outside the cell. When I say outside the cell, I don't mean another neighboring cell. I either mean the environment, if I'm a single-cell bacteria. So the cell's got a set of standards and solutions inside of it, and it's sitting in an area that will have solutions. Or it's one cell, interstitial fluid, extracellular solution, and then the next cell. So we're talking between cells or the cell and its environment. Because aren't those only two places cells can pull and remove things from a cell? Yeah. You're not going to be talking about the cell in Circle K. I always love my little brother to talk about evolution and evolutionary traits, and I'll ask a question about where do potentially beneficial genes come from? And I'll have kids say, they go and get them. Look at the gene store? Yeah, I really need some resistance genes. Oh, I know it's second how it would be. Start that line. Okay, so let's say we have a cell, and it has 5% salt in it, and the outside environment has 95% salt in it. What term do you want to use for the salt concentration inside the cell? Hypotonic. By default then, that means it's less than, the outside has to be hypertonic, more than. Are you with me?
Yeah.
That's how we use those. We're talking about just pure water. We're looking at just water. We pulled everything that's a potential solute out of it. And let's say the cell now has 95% water, and the outside has 5% water. You could use the term hyperosmotic for inside and hypoosmotic outside. What if they both have 5% salt in them? Isotonic and isoosmotic. Because don't you have to be equal in water if you're equal in solid? Okay, you can have more salt and less water. What is it, just in a package? So it's salt. Okay, so those are terms, and we'll apply them a lot, because that is at the crux of water's potential to impact the cells. So we're just scratching the surface, but the terminology is important to go, so when we say things like hypertonic, don't like. Anybody need problems with pH? Pretty straightforward. This is going to be important to us, because we have to be careful in biological settings, because if I start making hydrogen ions and hydroxides, here's your hydrogen ion and your hydroxide, are these reactive?
Yeah.
Yeah. Acids, not good. Bases, equally bad. So neutral is going to be where we have to sort of stay. Now we can fudge a little. Remember the power is the power of 10 each time you go up or down the scale on the pH scale. pH percent of hydrogen in its solution. But we can't deviate too much either way. Because do you agree too basic is just as bad as too acidic? Yeah, and it'll damage the cells. So there are going to be areas when we can do that. Clearly stomach acid has a pH of about 3, so we're going to talk about how we deal with that environment. Because that's going to be clearly destructive. But for us in our processes, when we start moving things and dealing with water and letting water disassociate things, in biology we have to have homeostatic mechanisms in place that we don't get cellular damage. So you've got all these constraints all the time called life. This isn't an anti-bio class or an abio class. So we can't, so some of the boundaries that were not there, let's say in chemistry, are now in place because you weren't worrying about maintaining life in a chemistry class. So you can go crazy all over the place, use acids and bases and create hydroxide, hydroxyls, and just go crazy, and we can't because if we do, we don't account for that. pH 202 will be. And don't forget, 5 power of 10, so each time you get 10 times more, not just 1 times more. So pretty quickly, between one area, you've got seriously more acids and bases to deal with. And we use them in biology, this term called buffers. You may have used these in chemistry, yes? Yeah. Did you, anatomy, physiology?
Yeah.
What these two? Yeah, so we use these all over the term to regulate. Probably one of the most common ones you've probably already seen if you've been in the phrase classified carbonate. It's a great way to make sure pH doesn't go too low when we talk about carbon dioxide, which we produce like crazy, has a slight acidic effect. So but don't care. These are just terms to make sure we're all on the same page. When we apply them, we'll talk more about them. But it shouldn't be too this gasping moment where you're like, oh, buffers!
What's the main buffer in our body?
Bicarbonate.
Okay, yeah.
Yeah, that's the most prevalent one. And again, the use of buffers, you can use them in any lab because if you're trying to control pH for whatever reason, you would use a buffer. But they have special meaning in biology because we have to have them internally. We have buffers all over the place with processes because we can't afford to start killing off cells. Okay. In a summary, you don't have to write this. Unifying themes. So those are sort of the big, giant umbrella topics that we can talk about that will sort of be woven into all the things we talk about, whether it's cell respiration, or if we're talking about adaptability, or we're talking about digestion, or evolution of a structure or function. They're all sort of interwoven all the time within everything we talk about. All living things have basic requirements. Those are the sort of characteristics of life or traits of life. So if they don't fit that somewhere, at least at a cellular level, then we don't talk about them. We have certain rigorous expectations, especially in this class, in terms of biology, that we need to constantly be aware of so that we're not deviating. We've got some biochemistry that's not organic chemistry. We'll talk about that later. We have a biochemistry that has to do with just we have to work within the limitations of chemistry, and that there's going to be water properties, so 7, that we are going to start applying to cells starting today. So far, so good? Pretty basic stuff. Okay, awesome. Let's get back to the lab then. And see how our little, how long has it been in our